My name is Chang. I think I introduced myself the first day of class, and I think we went through learning about ROS, SLAM, about robot manipulation, a little bit about planning, and now we are at a stage to learn a little bit about artificial intelligence, more specifically, computer vision. Okay, we want the robot to understand the environment. Okay, so it needs to, with a camera, which is a sensor, with the camera, it needs to see the objects, the obstacles ahead of the robot, that's ahead of or surrounding robot, and it needs to manipulate itself. So, yes. And of course, computer vision is not AI. AI is a lot more than AI. I mean, it needs to see, it needs to hear, it needs to have basic knowledge about the world. All of this is needed for having intelligence. Okay, so I'm going to be talking about object detection. Who has heard of object detection? Okay, so who has heard of YOLO? Okay. So this is pretty much going to be sort of a review, I guess. So out of the many possible computer vision algorithms, I've chosen object detection as one of the essential algorithms for understanding the surroundings. Okay. So object detection is you want to detect instances of segment objects or objects trained prior to its use. So here we see 3 pedestrians crossing the street. On the right hand side, we see also cars. So in order to detect person, cars, an algorithm was trained using data to detect humans and cars. And of course, detecting objects is an essential element for building physical AI. And there are many algorithms to perform object detection. YOLO, faster RCN, and there are many other detection algorithms. Who knows, anyone here know the difference between YOLO and faster RCN? I can give you a hint. YOLO is considered a one-stage detector, and faster RCN is a 2-stage detector. faster RCNN performs object detection by first finding out regions where there might be predefined objects. So it does, it has a network that finds proposals of the region, and from that region, it does classification. So it's a two-stage. YOLO is a one-stage. It detects, it finds the region and also classifies simultaneously. This slide is image segmentation. I think image segmentation gives all the information about our surroundings. Who has heard of image segmentation? Image segmentation is, so given an image shown here, A, it tries to classify each pixel as one of the objects. Okay. So, and there are various types of segmentation algorithms, semantic segmentation, instance segmentation, and panoptic segmentation. By looking at these examples, who can tell me what semantic segmentation is? So let me just tell you the little difference. Okay, there are a whole bunch of cars. There are pedestrians. There are buildings, the lights. In semantic segmentation, the cars are not distinct. There are several cars. The cars are not distinguished. They're all labeled as cars. And how do I know that? So blue color represents cars. Okay, so a light will be represented by yellow, pedestrians red. There's no distinction between the different cars in this picture. And if you look at here, you see that the different cars are labeled differently. But you see that other parts are not labeled at all. And that's instance segmentation, semantic segmentation. And here's panoptic segmentation. All the pixels are labeled. And the cars, different cars are labeled differently. The different pedestrians are labeled differently. So, semantic segmentation. So if you, in some semantic segmentation, you predefine a class, maybe 100, 20, and you just label it, okay? And without distinction between different instances. Okay, so all the cars are the same. Okay, and you see that the backgrounds are also labeled. The sky, building, these are sort of the ground are backgrounds. They are also labeled. Okay, so semantic segmentation is labeling each of the class that includes foreground and background, and that labels all the pixels in the image. In instance segmentation, you don't label the foreground or the background. You just label the classes that you could predefine, and the different instances are labeled different. So you know exactly how many cars there are in this image. There are 4 cars. Panoptic segmentation is a combination of semantic segmentation and instance segmentation. So it labels the foreground and background, and it distinguishes the different instances. Okay. I show you this because I think this is a much better understanding of the surrounding. But for simplicity, I'm going to focus on object detection. Okay, and the lab will teach you about running this object detection on the robot for the class that is not predefined. So you define your own class. Who has trained YOLO from scratch? Or okay, so that's going to be you. Okay, so there are different ways to understand the world. I showed you, there are probably many. Another way to understand the world is by sound, by maybe distance of objects from where you are, and so forth. But let's just focus on object detection and segmentation. There are pros and cons. If you do, this is in comparison with one another. Object detection requires much less computation than segmentation, for obvious reason, right? Because in segmentation, you're trying to label all of the pixels, essentially. And in object detection, you're just trying to find where your object is. By the way, I just want to define object detection. Object detection does two things. It finds the region where the object is, and it also classifies it. Okay? So it does two things. So that's one point for object detection in terms of computation. But what are the cons? Object detection obviously provides little information compared to segmentation. Segmentation provides all the information. There are different models for both of them, and we're going to focus on YOLO. But there are detectors that are much better in terms of performance than YOLO. Okay, YOLO is computationally cheap and it's fairly accurate, but there are algorithms that are much accurate. In terms of after you've trained it, how much flops, how much computation does it require to do detection or segmentation? 30 gigaflops for to run YOLO, and for segmentation, 33 times higher. I think the robot that we have can do about a teraflop of operation. And in fact, YOLO does 45 frames. It can do 45 frames of detection in real time. So, and it requires 1.4 teraflops. this one requires a lot more. I show you this because, in the project that you will be doing after this, you may want to run a segmentation algorithm. Maybe segmentation algorithm requires a lot of computation. Maybe you can implement something that is cheap. Maybe some approximation of the good ones. Okay, and maybe get some better performance. So here is instance segmentation detection. Let's see. Yeah, object detection is something that a lot of real machines do, like buses and cars, and a lot of them have object detections. Okay, so if you're sure about what you want to detect, I think object detection is okay. And this slide shows the inference cost and the hardware computations that's required for YOLO versus YOSO. YOSO is a segmentation algorithm, okay? And it does that in real time as well. And this is the robot that we've been using. I want to ask you, I said this in the very beginning of the course. This is the first time that we're opening this lab with this robot, and I would like to know your opinion. What do you think? Reasonable? Good? Do you learn a lot? So and so. Also, you can also run your object detector with a ChatGPT or LLM loaded onto this robot to enhance the performance. And I think you can do a lot of interesting things with this. I think we all had loss, so I'm sure that you're familiar with these notion. Loss is built upon a thing called package, okay? And the package has nodes. Nodes is like a program. Topic is communication between the nodes, and you're sending messages between these nodes. Okay. So, why am I showing you this? For object detection, why is this very important? You have a camera, okay, which receives for images, and that images has to be sent to the YOLO program. And the YOLO processes that image and then produces the output, and it sends it out. Okay. So YOLO is, I have a figure. So there's a camera node, which takes images, RGB images, it sends it out to the YOLO node, and the YOLO node does detection. So, let's talk about what YOLO is doing. Anybody here know how YOLO operates? Or let's assume that the image contains one object: dog, person, chair. How would you detect this object? Or not detect the object, or how do you know whether there is this object? Or how do you classify that? So there's an image, and you have one of the many objects in the image. What will be an algorithm to tell you what is in the image?
We can group similar pixels together.
Hmm?
We can group like similar pixels together, and
Clustering, you're saying clustering, yes.
and then if there is if we train the model on previously classified images of dogs, then we can compare that clusters and see how we can.
Well, you know, the dogs, there are many different size, different forms of, well, they're all four-legged, but I mean, the dog could be standing up, dog could be doing various tricks. How would you classify a picture of a dog? The word that I want to say is you want to extract out information that is distinguishable from other classes. So let's say I am trying to distinguish between a cat and a dog, okay? And cat could be doing a lot of different things. It could be standing up, it could be running, it could be jumping, and dog could be doing that. And there are different types of cats, different types of dogs. What you want to do is you want to extract feature, okay? That feature might be the length of the body with respect to the length of the dog's leg. That might be one feature, okay? And you may have sort of an average of all the different types of dogs doing different things. And you do that also for cats. So you have features, okay, these certain features. And then for a particular dog or particular cat, you extract that feature and you see whether it's closer to dog or to a cat. Okay, yes?
In order to extract that information, how would we then classify it? Let's say that if the leg is the classifying information that we want to extract, how do we know that it's the leg? And we have to do the same thing for that too, right? Where does that go?
Okay, so that's a very good question, and that was the question that I was going to pose to you. Who might answer that question? How do you extract out great feature? How do you extract out great feature that would cover different types of dogs doing different motion and for different cats? What would be a way to extract that good feature? So let me just tell you, okay? You take the image, so you have a whole bunch of images of dogs and cats, a whole bunch, maybe 10,000. Then you have a function, okay? And this function is malleable, meaning that you can change the parameters of this function, okay? This function, any function, actually, take a function and you set it randomly. You send each of the images, you apply that function to each of those images that you have, and that function is going to give you some output. And you're going to say whether that, from that output, you're going to sort of have a classifier, a simple classifier, that would tell you whether it's a dog or a cat. If the classifier is not predicting it correctly, you do a feedback and you modify the parameter of the function. Until the function gives you a good feature for to accurately predict cat and dog. And that's what we're doing right now. That's the state of AI right now. And what is that function that we use? What is the function that we use? Deep learning. Well, deep neural network. Deep convolutional neural network. That's the function. Okay? So we apply the deep neural network, or CNN, to this function, produce some output, and based on that output, we try to predict the classes. If we can't, then we modify the function. And we keep on doing that. Okay? So that's one image, that's one object. Are we always classifying one object in an image? We have multiple images. Okay. So, YOLO is an object detector that tells you where the objects are and what the objects are, okay, for multiple images. And how does it do it? It does it by dividing the image into many grids, as shown in this here, in this picture. So you can see that there are white grids, 1, 2, 3, 4, 5 by 4. 5 by 4 grid, and each grid is assuming that there are 1 or 2 objects in the image. Okay? So the first thing it does for each of the grid, it figures out whether there is an object or not, presence of an object or not, and if there is, it tells you the center coordinate of the object and the width and height of the box that will contain the object. And finally, it would spit out the probabilities of the different classes. Okay. So this is what YOLO would be. There are cups in the image, 3 cups, multiple images, multiple objects, and it's able to do that. And it's very easy to do. Okay, it gets the image, and it produces the class, probabilities, and the bounding box of the object. Okay. So, who has heard of convolutional neural network? What is a convolutional neural network? So we know what a filter is from signals and systems. We're all seniors here, seniors and juniors, right? So we have signals and systems. So we know that in order to filter a signal, we have filters, okay? So in convolutional neural network, we take an image. Okay, let's first now talk about convolution. Why convolution? We have an image, and I said that we need to extract out a feature that would tell you what object is it, right? A feature that would allow you to distinguish or classify the object in this image. Now, this function, you can think of it as a function, and the function is structured in a hierarchical manner. What do I mean by hierarchical manner? It takes the input, it processes it, takes the output, the next stage, process that output, produces an output, and then the next stage processing. So the input is processed, output, the output is processed by another function, different functions at different layers, until you get your final output. Okay, that's what I mean by hierarchical. Okay. Now, instead of a CNN, we can consider a fully connected network where all the images are connected to all the nodes here and so forth. But that would require a lot of parameters. CNN is an architecture where you save a lot of parameters. So here you can see this image right here. This is the output of this input using 2 different filters. This filter and this filter. And the filter is very localized, and that filter is moving around the whole image and producing that output. Okay. And that output, okay, is subsample. Anybody will know the word subsample? It's another word for pooling. And pooling, what pooling does is you throw out the output. You throw away output. Okay, so you have, it's shown here, 224 by 224 times 64. 64 means there are 64 filters. And that has been pooled, so the dimension has been reduced to a half. What is a good reason for throwing away samples? After you filter it, you get almost the same image or the same information after throwing away samples. So you have a signal, you have a filter, you filter it, you have your output, but you can throw away samples and your image, your information is still retained. Why is that? If you can give me the answer, I'll try to raise your final project points. You can give me any image, just try. Yeah?
Like the convolutional layer filter are shifted among the original image. So if we just like give up, 버리는 그 어쨌든 조그만한 정보들을 버려도 어차피 계속 옆으로 이동하면서 계속 이게 뽑아내기 때문에 옆에 정보랑
거의 차이가 없죠.
네.
Okay, so there's a lot of redundancy. Lot of redundancy in the image. Okay, because I'm running, let's say for instance, short filter, it's all 3 by 3. I'm taking average. Okay, I'm going to take an average. So what I do is I'm going to take an average of 3 by 3 pixels, 9 pixels. So it's 1/3, 1/3, 1/3. I do an dot product, right? So that's the output, and then I shift it. And if I shift that filter, okay, the output value is not going to change very much. Another way of saying that is that the filter is low pass, okay? Generally, the filter is low pass. So if I had a signal that's full spectrum, 0 to pi, and you have a filter, a low pass filter, you're going to throw away all the high frequency information. It's all gone. Okay? So what does that mean? After you filter it, you're using only a small segment of the spectrum. You're not efficiently using the spectrum. The spectrum has to be 0 to pi. It needs to contain all the information, and you only have information in a certain section. So your spectrum efficiency is low. Now, if you throw away samples in time domain, what does that mean in the spectrum domain? If you throw away samples in the time domain, that means expansion in the spectrum. So your efficiency, spectrum efficiency goes up. But anyways, that's a little bit more detail than you require. Anyways, you throw away. And one of the reasons is a lot of redundancy. That's very good. Okay? Then you keep on doing it until you want to get feature vector that is common for all the pedestrians, but very different from car features. That's the objective. to get feature for a particular class to be clustered, but that feature being very distinct from other classes. And you do that by changing the weight of the filters. You change the function. Okay? So with this, you could do classification, object detection. It's based on similar structure. You could do classification, object detection, and segmentation, and lots of other things. But the framework is very, very similar. And here is a picture of convolution, right? So you're doing inner dot product, you're shifting it, and doing inner dot product, and here's the and the output value, like someone said here, what I don't know his name, probably gonna give him some points. There's going to be, the values are going to be very, very similar. So you can throw that in. Okay. And also another way to say is spectral efficiency. So CNN uses a common filter to go through all the images, to go through all the regions. So a filter here, that same filter is moved here, here, here. A general form will be a different field filter that is dedicated to this region. But having so many filters would be too many parameters. You would need a lot of data for that. Here is word ReLU. Convolution is a linear process. Okay, it's a linear process. I hope if you have signals and systems, you know that it's a linear system. Okay. If this whole thing was a linear system after another linear system, what can you do? And you can combine it into one linear system. Okay. But it isn't a one linear system. It's linear and non-linear. Linear and non-linear. I mean, because this is supposed to mimic our brain. Our brain is not a linear system. It's not non-linear. And I hope everybody knows what a ReLU is. It's a sort of a rectifier. When it's negative, it spits out 0. When it's positive, it's a linear output. Okay? So it's a network of convolutions, ReLU, and then based on that output, you get your feature, you do classification. What's the classification that you know that a lot of people use? What's a classifier that you know is good? And I'm assuming that everyone here has had a little bit of AI, whatever. Softmax. Okay, I hope everyone knows what softmax is. Softmax let me just say, for some of you who don't know what softmax is, you take your feature, you do an inner dot product, and then you exponentiate. Okay? So you do an inner dot product that is specific to the different classes. So I'm doing, let's say, dog and cats. Dog and cat would have a different vector. And you take that feature and you project it onto different dog feature or cat feature. And then you exponentiate and then you normalize for different classes. That's all it is. And then that would be like sort of like the probability of being a dog or a cat. This is, so here is a dog, and this is a particular detector, not a detector, but classifier actually, and this is the sort of the output. Okay. And this would be low-level feature, high-level feature, a mid-level feature, high-level feature. This feature that's localized of that dog. These local features are combined to give you sort of a higher mid-level features and so forth. Okay. How do you get these features? What would be the good answer? How do you get a feature like this? How do you get features like this? Once you've trained it. You trained it so that the output feature, from that output feature, you can do classification fairly accurately. How do you get these features? What you're doing is you're finding the weight, you're doing inner dot product with the weight and the that will give you a feature. And the second layer would have a different weights. And it would have a wider scope. Okay, I've said pretty much everything about YOLO. YOLO is not a two-step detector. A two-step detector is, in the first step, you get region proposals. You have a network that gives you possibility regions of locations of the objects, possible locations. And then there's a network called RPN. Okay. And based on that proposal, you do classification to find out where the objects are. So it's two-stage, RPN and then classification on proposed regions. Okay, that is fast RCN, faster RCN, and that tends to be more accurate. What I'm going to focus on today and also in the lab will be YOLO, which is not two-step, it's one step. There is no proposal stage. Okay? YOLO was first proposed in 2015. It's evolved, and now it's YOLO version 12. It's fairly accurate, Much has been improved. Also, this this thing about, I see this picture, so I'm just going to talk about it. So here is a dog and a bicycle. And I have predefined as one of my classes to be dog and bicycle. Okay, actually YOLO can find 20 classes, 20. Okay. Dog and a cat. Now you look at this thing, and there are many possible boxes for the dog and for the cat. Many. Okay? But we don't want many. We want one clean one like this for each of the objects. How do we do it? What will be a good algorithm? You see, for that bicycle, there are so many boxes, possible boxes. For that dog, there's also many possible boxes for that dog. And that actually comes up in YOLO. How do you choose one that gives you the best possible? The algorithm, it's common sense. Each boxes come with the confidence or probability of that object. Okay? So you look at all the boxes and you say if the intersection of union, IOU, that's what we call, okay, if the boxes overlap considerably, maybe 65 or 70% if the boxes, then they are boxing the same object. They're boxing the same object. And then, you say that, okay, so they're all saying that it's going to be some common object. And then you look through these common boxes and say which one says with high confidence that it is some object. And this yellow one won because it said, I'm pretty sure that this is a bicycle with higher probability. So out of the many boxes that there is shown, that one is chosen. Okay, so this is a slide about, detection. There's two-stage detection, and there is one stage. YOLO is one stage, and as I said, here is two-stage RCNN, faster RCNN. These are two stages. Obviously, this is going to be a little bit more accurate, but it's going to take more computation. And we're going to focus on this, YOLO. Okay, but for the project, if you want to do well, because there will be important guests at the evaluation day, and you want to impress them, you may want to go two-stage, because that's going to be a little bit more accurate. Or you may want to do segmentation to be more impressive. And of course, so there are pros and cons for this. And I'm really hoping that many of you are adventurers and risk takers. Huh? And try out some crazy difficult algorithms. Huh? And you know what the project is going to be? You've learned the basics, this and that, and you know that also the system provides lots of basic algorithms. So with that, we're going to show you sort of an environment. So we're going to hide it, and then on a certain day, we're going to show it to you and ask you to perform that, to perform a certain task in that environment. And yes, this is, YOLO, 45 frames per second. Oh, this is, what is that, 45? This is, what is it, 27, 28? And this is YOLO version 6. Right now we have version 12, so it's going to be much better than this. Oh, this is 45 frames. Yeah, a lot of current algorithms use YOLO. A lot of self-driving cars, various robot demos are using YOLO. Video surveillance, augmented reality, virtual reality, video based on YOLO. And this is the function. The function is a convolutional layer, okay, to extract out the feature. 24 hierarchical layers. This is for version 1, okay? And it takes image size 224 by 224. And 7 by 7 by 30, 10. What does this mean? What does this mean? Can someone tell me what this means? What does that mean? I said something. And I will. Give me a guess. Give me a guess.
It's the final dimensions of the bullet vector view.
Yes, it's going to be the output. Well, why is it this? What is this supposed to mean?
I think you can interpret as two vector. First is 13 feature map with the size of 7 on 7, or you can.
Yes, I know that. Well, what is 7, 7? What is that supposed to mean? I've given you a hint.
There are 30 filters.
No. I said there's just 24 convolutional layers. There's going to be more than 30 filters, I think.
The original image divided by 7, 7,
7, 7, yes. There are 7 grids, 7 by 7 grids. Okay? And I should just tell you about this 30. Now let's look. For each grid, it tells you the probability. Oh, actually, this is a little bit different from. Okay, so this is, assuming that there are 20, probability of 20 classes. Actually, first of all, it says whether there is presence of an object, yes or no. Okay? Yes or no? Second, it's the bounding box. The center point or the midpoint or of the object, that's x1 and y1 of the bounding box in the grid. And this is the width and height of the bounding box in the grid. Okay, so that's 4. And also the class probabilities. So if there are 20 classes, so in YOLO, we're looking at 20 classes. So it gives you the probability of each of the 20 classes. Okay? So each of the 49 is going to give you these things. And that is, I think, 30 lengths long. Is that correct? Is that correct? Yeah. So that's, so this is actually, it's going to be 30. So here it is, I see. There's 24 classes. And it's going to assume that there are at most two objects in the grid. That's one object, and this is the other object. So that's 25 plus another 5, that is 30. Okay? But you can do 13 by 13, you can do other things.
Professor,
Yes.
I verified the original university with 7 by 7. How do you project the nearby boundaries with boundaries?
Yes. So you are going to also combine. So that's a very good question. So because there's for instance, you're not going to get, if I divide this dog's going to be divided into many centers, right? And it's going to say, it's going to look at a piece and it's going to say, oh, it's a dog. That's how it was trained. That's how it was trained. So you can look at a piece and say it's a dog. 학습을 그렇게 했기 때문에 해석할 때도 Okay? So here is, what was it, 7 by 7 case, 20 cases, 2 bounding boxes, and it's the confidence of that. So, each one would say, this one would say cat, this cat, and so forth. Okay? But after you see this cat, the center point is here. So this one will be it. Okay, so this will say, oh, the center point is here, or whatever. But there will be all cat, and we know that this will be all cat, so this will be one cat, and this one will probably have, this block will have the width and the height of the box. that's pretty much everything that I have to say. It's the same thing. I've said this, many boxes, and you choose the one with the highest confidence. If there are many boxes, possible boxes, okay? And we call that non-maximum suppression. And for training, I hope everyone knows what in AI, we have a training stage and also inference stage. We call that test stage. In the test stage, we put training data, okay? And we have a loss function, and we update the function. We update the parameter of the function in the training stage. Okay. And this is the loss. This is the criteria of how the functions are updated. So in the training, I have data with labeled boxes, okay? So I know where the center point is, and my predictor will give me the center point. That's the prediction. There's a hat missing here. It looks at the center points, and it's checking whether it's close or not. It's looking at the width. It's also looking at the height. Okay, it's checking whether my predicting is correct. So this is, I have it. This is the ground truth of the training data, label of the training data. This is the label of the training data, label of the training data. This is sort of like the class, and this is the probability of the different classes. Okay. I'm checking whether my predictor or my function is producing the right output. It's looking at this value. If it's not, then it's updating the weight of the convolutional neural net. What is an algorithm? What is an algorithm to update the weight of the convolutional neural network? So in the lab, are we going to do back propagation?
Yes.
We're going to do back propagation in the lab for different class. Okay. And this is ROS. You can run ROS on ROS 2. You can learn ROS 2, and you can set up YOLO by creating this package called YOLO detector. Okay, ROS 2. The basic building blocks are the package, right? And then you also have to set up the communication between them, the nodes and so forth. And you can do that. And here are the TAs to help you for you to go through this. So YOLO. So the pre-trained YOLO is available, okay? But we're going to ask you to add additional classes. Okay? So that would require you to train it. Okay? Train it for your specific task. Okay? So you can do the project. There are many references, No, I'm supposed to have only 1.5 hours, so I'm 5:20, I'm close to. But there are various detectors, classifier detectors, okay, that you can read. And there are also YouTube. I looked at the YouTube. I also looked at ChatGPT, you know. Use whatever is available to learn as much as possible. ChatGPT knows Ross too very well. Very well, so, you know. Any questions? Yeah. No. Okay. So, you know, I'm the person who designed this course. I invited all the professors. Okay? And I'm the one actually my TAs researched the internet to find the appropriate robot. Okay? This is the first time. I don't think there is a course like this in this whole world. Okay? That would allow you to put these AI algorithms, ChatGPT into the robot to do various tasks. Okay? And I'm really hoping that you can do something amazing on the project day. Because I'm taking a risk, but I'm going to invite some very important people on the evaluation day. And I would like to see something crazy, something wonderful. Okay. So, you know, I'm supporting all of you, and I really hope that you do really well. Okay? So that's it. Any questions? No questions? Okay. See you next week.